There have been thousands of exoplanets been discovered so far, but how do we actually get the shape of them? So some of them we know are elliptical shape, some of them are more spherical shape, but how do we actually know what their shape is depending on how much light they block out? Well, we're going to have a look at that and then have a real example at the end to show how we found out that it's actually elliptical in shape. So firstly, the basic transit shape for a spherical planet looks a little bit like this. So you get this typical U shape dip in brightness. So as it passes in front of the star, it blocks out light in this symmetrical manner. If there's no exomoons there or anything else, or any other planets in the system, then you'd always get the same sort of transit each time. And it blocks out light in this manner, really, which is fairly typical. But as the planet changes shape, so it becomes more elliptical, then that transit shape also changes as well. So that typical spherical U shape we get from the spherical planet is no longer applicable. The difference isn't massive, but it's enough to detect the shape of the planet. So this is an example of a Jupiter-sized planet, which is orbiting the star around about the Roche limit. So here you can see that actually as it transits across the star, what we see, its cross-sectional area, is changing, and it's the least when it's bang in the centre of the star, so it's in line between us and the star, and it's greatest towards the edges. So first, let's just have a recap of what the Roche limit is. So the Roche limit is a limit or a distance from a more massive object. So the example here is going to be Jupiter, and if we had a moon, and if it got close to the Roche limit, it's going to get stretched. The strong tidal forces from Jupiter start to stretch it. Now, once it goes beyond the Roche limit and it's inside it, then the internal gravitational forces of the moon is unable to hold it together, and it actually gets pulled apart. So that Roche limit is the point at which it would be pulled apart by the strong tides. So if we have a planet around about at the Roche limit, we would expect it to be elongated in the direction of the planet, or if it's a exoplanet orbiting a star, we'd expect that exoplanet to be elongated in the direction of the star. Now, another consequence of that is those strongs are likely going to cause a tidal locking as well. So that means that the rotation period matches the orbital period. So it will rotate once on its axis for one orbit around the star. So it always has the same face facing towards the star, and it will be stretched towards the star as well. So we would expect this sort of shape and this sort of behavior, really. So it's always going to have this orientation as it goes around. So here you have a spherical and an elliptical Jupiter-sized planet that have been modelled on how it would actually block the light out. Now, the red line is the elliptical planet, and the dotted or dashed line is the spherical one. And you can't really see a huge amount of difference here. There isn't a huge amount, but you can probably see at the bottom there's a slight difference. So what we can do here is, if we zoom in on that section there, then you can see the difference between the spherical and the elliptical shaped planet here. There's more deviation in the middle. So we can see that one is blocking out more light than the other. Now, why is that actually the case? Well, first let's have a look at the difference between the two. So what we can do here is we can subtract the elliptical model from the spherical model, and then we end up with this here. So this is the difference between the two models. And we can see that before it transits the star, no difference. And then as it transits in front of the star, it blocks out more light, less light, and you get this variation here. So just to kind of explain where that comes from, when it's directly in the middle of the star, it's going to be orientated so that the stretching or elongation is towards the star. So the surface area that it's blocking out of the star is going to be the least. So we get this point here on the graph where it's blocking out the least amount of light. And when it's towards the edges, because it's orbiting and it's likely tidally locked as well, and that stretching is at a slight angle, so the planet is slightly angled, then it's going to have a bigger, slightly bigger surface area or cross-sectional area that's blocking out more light of the star. So we get a difference there compared to the spherical model, whereas the spherical model, the actual area of the planet that's blocking out the light doesn't change. The variation comes from the variation in the star, which is from limb darkening. So it's due to the orientation of that elliptical planet as to why it blocks out more or less light, and you get this typical shape here if it's elliptical compared to the spherical one. So a real example then is Wasp 103b. So here's the transit from that, and from the transit they were able to detect that it was about 1.5 times the radius of Jupiter. So this is it's a big planet. It's not a small planet at all. And how did they work out that this was actually elliptical? Well, again, they ran spherical and elliptical models. They obviously looked for the difference between the two, and they compared that to the real data they got, and they were able to determine that this was an elliptical planet. So again, the green line here is the differences between the spherical and elliptical models, and again, the actual observations themselves, you can see which is the lots of the black dots, and then the best fit line is the blue line, and then the green is kind of the difference between the two, and that is what has led to the determination that this is a elliptical planet, is that you can run a model if it's a spherical one, and then you look at the real data and you can work out that actually deviates away from that slightly in this manner, which relates to this elliptical planet, which is likely going to be tidally locked as well. So again, with this planet, the strong tidal forces are going to stretch it towards the star. It's also very close to the star, which means that the stretching is going to be quite significant, and it's going to be this elliptical shape or ellipsoid. And because it's so close, it's also about 20 times hotter than Jupiter. So it's a very, very hot planet, and that is because it's so close to that star. It's also going to be tidally locked, and it will have one very hot side compared to the night side, which will still be very hot, but won't be as hot. So a very hot planet, very unusual shaped planet, and a fairly large planet as well. So thank you for watching, and if you enjoy, then check out some of the other videos.